most popular one which are used in the case of GPS, mainly the Earth center, Earth fixed, Earth center inertial, orbital. So we have also seen the conversion between two, and why the conversion is required, because we are considering the satellite motion in Earth center inertial frame. So that was the first lecture. Then we move on to the signal structure, the basic principal positioning. What are the signals those we are using in the case of GPS, or the information which is modulated on those carrier which is available to us. And then we have seen some of the applications in terms of what, if you have a GPS, what type of application you can do with the help of static, kinematic, DGPS mode, RTK mode. And then we also have seen the mathematical model yesterday of the chord pseudo ranges as well as the carrier phases. So today we are discussing some of the error sources which are prominent one, and so the estimate, precision in the estimates also depends on those biases which the signals is facing from moving from satellite end to the receiver end. So it moves. So obviously the satellite part, there are certain delays because there are certain errors, because of which we have certain errors in our position estimates, and because the medium it goes through, it has certain effects on those signals. So we'll understand these particular errors. First we see the errors in the GPS observation, which can be categorized in terms of gross, systematic and random errors. So obviously the loss of a satellite signal lock, which is whether the cycle slip, the point where the cycle slip occurs, and the moment it occurs, your position or the carrier phase observable which you plot goes out of your out of the sync. Corruption of GPS signal due to any power line or objects having magnetic characteristics, improper leveling or centering of receiver antenna. So these we generally avoid. So errors in measuring height of the antenna center from the ground, which we have discussed also in the few the labs, that we have to properly measure this antenna center from the ground. Some of the systematic errors we have also seen in the phase residual, that some patterns are biased towards a particular trend, that satellite related errors, receiver related errors, signal propagating errors, and some of the random errors because of the instrument noise. So these are basically categorized based on the effect they are doing. So we'll start from the satellite end one by one. We'll try to accumulate the understanding what kind of effects are there, so that could eventually degrade our signal. So satellite dependent. So some of the you already understood that the satellite is moving in an orbit, and because of the perturbation, there are so many forces acting over it, and because of which certain drifts occur, not only in the satellite clocks but also in the orbits. So the orbital related, which we call it ephemeris error, and the orbit perturbation. So these originate at the satellite end and found to be part of satellite transmitted signal. So the navigation message which is coming as part of the information from the satellite end has this kind of information about the ephemeris. So the broadcast ephemeris, if you are using those information to generate the so-called satellite orbital estimate for the position of the satellites, you could see the effect of those errors. We'll also see some graphical representation of those errors, what will happen if those changes. And this is the major source of error, which we call it satellite clocks. So if you haven't accounted the drift in those clocks because of the factors of the, so this may cause a lot of error in the range estimate. So eventually it will degrade the quality of the position estimate in your receiver position. So selective availability, since it is off, but we will also see what will happen if the selective availability is there, and how much the clock error could be there purely because of the selective availability. Then moving on to receiver end, which we call it receiver dependent, is because of the receiver clock, because something happens to the receiver and it goes turned off. So cycle slip may occur, some of the receiver noises. So these are originated from the receiver end. Observation medium dependent. So the propagation medium, because of the ionospheric and tropospheric effect, we have these two major delay which are properly estimated and removed well before we estimate the position. Some of the station dependent, which we call it multipath antenna phase center movement. So multipath is nothing but when the signal get reflected from another source and goes back to the antenna. So it will be eliminated well before, or you choose a different kind of antenna could help you in removing those multipath well before. And obviously the antenna phase center movement, because of which certain drift is there in the estimate. So from the satellite end, so now with the help of those navigation message, in general understanding we have a sheet of different parameters in which those Keplerian elements, some perturbation forces, the anomalies because of those. So everything is written in a proper navigation message. What we are doing, we are taking one by one to understand whether I am estimating the actual satellite position or not with respect to that particular epoch. So which we call it the satellite clock drift, because of the different forces acting over it. So when we consider the relativistic effect at the satellite end, so what will happen, the satellite clock, when they were launched from this so-called Earth to the particular orbit, so what will happen, their fundamental frequency is set slight below to that 10.23 megahertz. So their fundamental frequency, which we have understood from this literature, is that it is 10.23 megahertz. So it is set just below 10.23, because we know that because of this, from the Einstein general theory of relativity and a special theory of relativity, is that the clocks move faster when they go in the orbits. So because of which this slight below fixing of this fundamental frequency, when it goes onto the satellite, it automatically achieve this 10.23 because of this faster movement related on the surface of Earth. So, and obviously the drift because of the forces, so those two are well accounted, and around 14 to 15 meter range error could have been avoided if those errors could be properly taken into account. So satellite clock drift, and obviously those the parameters which you could use, which are coming through the navigation message, which we have discussed yesterday, also A0, A1, and A2. So you could compute those DT term with respect to the satellite. So you could estimate the corrections which is applied to the satellite. And it is a general sense of understanding also that that's why you are taking into account that satellite clock bias is properly known well before you take into account the XYZ and the receiver clock offset. So one of the reasons that the satellite clock error, which we consider as well before known, because the parameters we are using to account for those are properly given. Second, obviously the ephemeris error. So what the master control station is doing, it is collecting data from all monitoring stations distributed around the globe, and it collecting the information from those monitoring stations, and it is predicting the satellite ephemeris well before. And after, there is a process called Kalman filter, which is applying from at the master control station. It is taking those parameters which is already coming to the satellite, and it is collecting from monitoring station. It is predicting the orbital parameters, or which we call it ephemeris, and it is sending to the uplink station so that it can communicate to the satellite. So if the satellite is drifting away from its orbits, it is getting information from that control segment, or which we call it the master control station, that okay, now the next few parameters for the next few couple of hours would be this. So they eventually turn and fit to that particular path which they should be. So that's why the master control station helps us in these upper two the error sources. However, since the selective availability was off, we are not much concerned about this at this stage. So similar to this, the other components are also which are very relevant to understanding of, before understanding the error sources, then only you can move for the position estimate. Okay, so this is a general figure which the estimates are given in terms of range term, because ultimately you are estimating the pseudo ranges through these the codes as well as from the carrier phases. So the satellite clock offset could be, so it is written as should be maybe around 300 kilometers. So based on this, you could see that the moment the signal emits from this position, and satellite moves well before in the space. So because of this, if your clock estimates are poor, you could be, you are prone to this much error. But we know the certain kind of error sources that could be, because of those navigation messages, you are removing or reducing this kind of error component from the range. Simply satellite instrumentation delay, or total group delay which we call it, those all could be removed well because of the information which is coming from the satellite end. Similarly, the geometric distances of this order, because of the ionospheric, this much error could be there, in the range measurement. Because of the troposphere also, this much range 2 to 10 meters could be there in the so-called the range measurement. Similarly to this, since the clock are very sensitive, if you have a, as we discussed thoroughly in the course, that if you have a nanosecond kind of error in your clock estimates, how much would be there in the range. So you could eventually multiply that by C. You could see if what could be the error in terms of nanosecond would be propagating to that particular range. So these are some of the error sources which systematically changes from one epoch to another. So these are the prime sources of errors. So they are properly categorized also, which we call it orbital errors, signal delays, increase in received frequency, error in observed VAR. So see, obviously they are from different end. So at the satellite end, some clock, satellite clock, selective availability, solar radiation pressure. So these are we properly monitor, and we try to see that these effects could be minimum as possible after the estimation. So there are two services which we couldn't cover in just by saying this, is precise point services and standard positioning services. So when we using code, CA code, we are actually working in the SPS, and when we are using the P code, we are actually working in the PPS. So because of these two services, the codes we are using, they are differentiated or classified into two categories. So satellite clock, if selective availability is not available, and with selective availability is available. So this could be more, eventually more, if with selective availability. Satellite perturbations, orbital ephemeris prediction. Obviously, you could see that with the help of availability of the satellite clock, you could see the component which could be more. So at receiver end, receiver noise and resolution, multipath, other interchannel biases. So based on these, the component you could see in the precise positioning services and standard positioning services, you have the different components in terms of meter. So, and yes, a UERE, which we call it user equivalent range error, when the individual component of error is converted to a particular range term, we call it user equivalent range error, and that is really helpful in understanding that the relation between DOP and the UERE. We'll see that part later. So as we discussed the satellite clock biases, the relativistic effect on satellite clock, time dilation, and because of the eccentricity of the satellite orbit. So those could be possible just because of the eccentricity of the orbit. If you don't account it, it may be more than a 14 to 15 meter kind of order in that range measurement. So obviously the satellite clock drift, that since the 3 time system which we are discussing from the day one is that one is the UTC, which is the leap second are introduced to the UTC to account for the earth rotation. One is the atomic clock, which is very standard time, and one which we call it the GPS time. So one time which we call it GPS time, we are taking the measurement of the time with respect to that GPS time. So that's why the satellite clock drift, which is nothing but the permittable allowances, or you could say that it is allowed to drift only 1 millisecond. So also the the clocks at the satellite end are very stable. They don't deviate much, although the threshold is 1 millisecond, but they are well within that threshold. As well as it is within 1 microsecond with the UTC. So the clock drift parameter are properly estimated with the help of navigation message. So this part is properly accounted when we are measuring the ranges. Similar to receiver clock biases, you have the cost crystal clock at the receiver end, and because of which you are actually estimating the clock offset of the receiver in terms of the estimation when we are doing from pseudo ranges or from the carrier edges. Okay, so you could see that some of the deviations in the clock error with respect to the so-called relativity effect as well as the drift. So you could see the trend also, and the similar to that, with if selective availability is on, this much nanosecond is the drift which could be there, and currently it is in 5 nanosecond. Now IGS provides precise satellite clock products which could be used directly for the called PPP, which we call it precise point positioning. Okay, so in the case of medium which we are discussing is that, so the satellite signals is now transmitted at the satellite end, is now propagating in the medium. So it starts with the so-called ionosphere, which is from the 50 kilometer from the surface of Earth to 1000 kilometers. So that particular area which we are discussing here is we call it ionosphere, and the four region properly from which we call it C, D, E, F. These are region is properly categorized into it. So generally in the daytime the C or D regions are active, and which we call it because of the ionization of the gas molecule. So the electron components are released. Electrons are released. So because of this reason, the daytime is highly active compared to the night time. So yes, it is the first part of the atmosphere that the signal encounters after transmitted from the satellite end. The electron density of the ionosphere changes with the number and dispersion of free electron released by the ionization of gas molecule. So these will see that part is that it is also measured as the total electron content which is available in a per meter cube. So the total electron content, which is a measure of number of free electrons in a column through the ionosphere with a cross sectional area of 1 square meter. So we account those total number of total electron content. We estimate the delay because of this in terms of V. So yes, ionosphere and sun has a proper relation, because when the sun activity is at peak, obviously you could understand that the ionosphere content would be delay because of the ionosphere would be more, and obviously the chord pseudo ranges get delayed and phase gets advances because of this phenomena. That you have the minus and plus term, which is in the chord pseudo range you have minus I, and the phase you have plus I. Obviously the ionospheric effect would be related with the satellite elevation also. So the moment satellite sets up or rises up from the horizon and goes beyond your zenith, the ionospheric error would be more in terms of the horizon compared to the zenith. So ionospheric effect for the chord pseudo ranges and carrier phases. Chords appears to be slowed, that's why we have put in the minus sign, and carrier waves itself appears to be speed up. What are the ways we could remove those delays? Because it is dispersive in nature, it relates with the square of the frequency in inversely proportional manner. So we use those relation and we try to accommodate. What if you have a single receiver only? So there are certain models, which one popular model which we call it GLOBK model, which we could use to remove those error term because since we don't have access to second frequency. So when we have dual frequency, the relationship between single frequency and dual frequency could have been used so that you could eliminate the ionospheric term, just we have done in the ionospheric free combination in the previous lectures. So yes, in ionospheric effect could be removed because of these dual frequency nature, and that's why the quality of estimates improves. However, when you use this combination, we are only reducing the effect. We are not totally removing the effects, isn't it? So the reducing is that up to what extent you are reducing it. So that's why the new strategy which we are popularly using, which we call it DGPS also. So the DGPS word says that if the baseline distance between base station and rover increases, you are not very sure that how much atmospheric effects are being cancelled out. So that's why when you are using the word, using the DGPS, you have to have a limit on the baselines, isn't it? So if the baseline increases more than 200 kilometers, you cannot be very sure that once you have performed the DGPS, the error because of ionosphere have been accounted or not. So that is one way you could see that differencing of observable is also helpful to a certain extent. Okay, so this we have already discussed, the linear combination of the phase, and because of this we could derive at an observable from L1 and L2 that could be ionospheric free. Similar to the tropospheric reflection, although it is non-dispersive in nature, it doesn't depend on the frequency of the signal, but it has certain components which because of which if you don't account them, the delay would be there because of the tropospheric. That those two components are categorized into dry and wet. The so-called the advantage in the case of dry delay is that it depends on the pressure. So you could have an relationship with respect to the surface pressure, and you derive an equation which could be helpful in removing those delays because of the troposphere. Similar to this, the wet delay, because many of the application of the GPS is estimating the water vapor content in the atmosphere, and because of this, the second part, which is we call it wet component, and if we indirectly we are estimating this second component, and that's why we could use the application of water vapor estimation. Secondly, if you don't have access to this the so-called those estimation the models which are available. So one model you could have the Sustemonian model, another is Hopfield model. So basically these model actually take into account all the parameters where on the which the atmospheric delay or in specifically the tropospheric delay is dependent, and they with the help of use of this model you could estimate those the delay in those ranges. Second is antenna phase center offset. Obviously, the antenna phase, what do we call it? Antenna phase center is the point where the radio signal measurement is referred to, and it is not necessarily the geometric antenna center. So, as the manufacturer develops this antenna, it is actually varying where is your ARP is there, which we call it antenna phase center. So, because of which, yes, the error occurs, and when we set up the antenna using it, we set up the antenna actually using the antenna using its geometric center. So when we take the height from the bottom of antenna or from the antenna phase center, that also is helpful in understanding that because of this we account certain errors. So if we don't properly measure it, though obviously we are prone to errors. So yes, again, next is multipath. Multipath is nothing but it is the direct path of the signal, and this should be avoided. So one of the best ways to avoid, choose your station very wisely, isn't it? So in the urban area which we have, skyscrapers are there, so we are very prone to multipath error because of the indirect path which is coming. So the signal has this property which we call the signal is right-handed circularly polarized. So if you slowly see the signal, it is coming in this manner to you. So if it is reflected by another surface, the RHCP, which we call it right-handed circular polarized, changed to LHCP, and if your receiver or antenna is not capable of detecting the so-called the RHCP or LHCP, it will account all. So obviously you could choose an antenna also which in an area where the multipath scenario is more. So one example is we call it choke ring antenna. It helps in detecting those LHCP or filter it out and give you the best possible signal from the satellite. So obviously the best solution is choose your location GPS site carefully. That's why major of the IGS sites, if you see the Hyderabad sites or if you see the IAC sites, they are in the remote areas, isn't it? So because to avoid these kind of errors, and we have seen some of the residuals also in some of the station that because of the multipath effect, the residual is deviating. So you could see in the DPH file also that because of those multipath, the effect is there. So this figure I leave up to you. You try to see and try to relate. Reference is not coming up. It's by Professor Per Enge from Stanford University. So this figure you could relate one by one. This is the satellite clock error because of selective availability. You could see the deviations which are there for quite a few hours. So these deviations could be limited if you don't have the selective availability. You could also relate with the other figures. I'll take 2-3 minutes. You could see that what are the error sources which are there if you have this kind of figures before you. What you understand from those two figures. What you understand from, let's say, if you are going for this figure, what would be those jumps if you could understand these two jumps. This is ephemeris errors. If you have ephemeris error in your understanding, what could be those jumps? Loss of log would be in the when you plot certain thing, or which parameter if you plot, then you could only see the cycle slip. This is ephemeris error versus time, not the phase versus time. Please focus on this word, ephemeris. Orbital. Why this jump is coming? If this is the kind of jump as you are expecting in your daily file, then would it be possible to and okay, what you are relating with this error term? What error it could be? We are not specific about any one parameter, because if it would be possible to plot every plot for with respect to time, isn't it? It is not plot of pseudo range. So we are on the on only the at the satellite end, and we have two major error sources. I'm not talking about all. We have two major error sources. One is if you have satellite clock drift. So we have already seen because of selectivity. Now it is not there because it is turned off. So now it is within. It is within. If you say it would be, although it is written in terms of meter, but it would be in, if you try to plot this in nanosecond, it would be plus minus 5 nanosecond, isn't it? Now because of selective availability is off. But here is that your ephemeris gets updated from the master control station. So your position of satellite also gets updated. Are you relating with this fact? Because master control station is collecting data and daily uploads are there to the satellite end from the uplinking station. So broadcast ephemeris gets updated in terms of those parameters. The moment you use those parameters to have an estimate of x, y, z of the satellite, and the moment you have next ephemerides, you have x, y, z. So possibly there would be little shift in the position of the satellite in terms of ECF coordinate system. So because of which you have little, is it?
Yeah.
Yeah.
Every 2 hours, say. The uploads only happen every 4 hours, but every 2
It
hours
is
they
the
do a new representation of it.
a new
And
representation.
because it's an approximation to their more complicated model, you get these little discontinuities and boundaries every 2 hours or so.
If it is using the updated parameters, then why is the error going up at breakthrough point?
Error going up.
Like the time at 2 hours.
And why does it go up?
Yeah, why is it going
Could have gone down. There's no reason it goes up or
that's
down.
kind of it.
And some days you won't see it, other days it will be worse. It depends on what the model is like. And this presumably is relative to a precise ephemeris. So you could actually do this yourself. You have all those broadcast ephemeris files. The interface control document for GPS tells you how to take the numbers in that file and convert them into XYZ coordinates. And you could difference them from the SP3 file coordinates and just see how they behave. So it's a fairly, in fact, we have software called OBDIF in the software package which allows you to difference SP3 files. So you could play around with this.
Yes, actually, those who are from IT Kanpur, they actually have certain labs on how to read the SP3 file and have a scatter plot or the polar plot of the satellite motion. So they actually try to see the difference between the navigation message, broadcast ephemeris and the precise ephemeris. So the data is uploaded after 12 hours.
Yeah.
So this gets updated.
Yeah, the full model they use is quite complicated, and so they have a very limited amount of space they can transmit it in. At 50 bits per second, you think about what your current gigabit internet rate is, 50 bits per second is a very low rate. So they have to make it a simplified version to get it into the message format. And so inside the satellite, it recomputes those numbers every 2 hours to get a better representation to the more complicated model that's being uploaded. But there's always this little discontinuity that happens because the parameterization. So it's essentially like having something which is quadratic and you produce linear fits to it every 2 hours. So when you do that, you can fit the linear, that little bit of the quadratic, but when you go to the next 2 hour chunk, that new fit is not going to line up with the old fit. And that's essentially what they do.
Okay. So now the next part is on understanding this tropospheric delay, because eventually that would be helpful to relate with your GAMIT session. Why would be, no, goes up to 15, here also of the same, and here it is near about 5 meters. Any clue of because actually this is helpful. Theory is not helpful. You would have to relate with the error sources.
Maybe due to the satellite rising in near the horizon, in horizon effect.
Yes. So at this moment, if satellite, rises up from the horizon, the errors would be more, and it for some period of time within that 15 degree, you have, isn't it? So I mean that is one way of looking at the figure, isn't it? And similarly, yes, if you want to.
No, I was just going to say there is a program in GAMIT called CView, which we don't talk about, but it's an X Windows interface, and you can actually sort of make that sort of plot based on the data that's there, and things like the multi-path error you can see. So if you want to explore that, it's interactive. So if anyone wants to talk about it, we need to actually save some files that we normally delete when we get processing the space data. But it's useful to do if you want to
Yes.
look at data.
And similarly to the ionospheric delay also, you could see or you could relate the two shift between the two delay the below one the estimation and with respect to the top one. So if you are using, because satellites also send certain parameters which take into account about the atmospheric term. So because of which when you are using the broadcast ephemeris data, you could use the GLOBK model where this alpha and beta terms comes up. So because of which the error which is estimated would be little higher if you use the, but you could see that still there is a component. So that's why we use the word reduced instead of removing. Isn't it? So, yeah. So the
problem is that model gets rid of about half of the error. It's not that good.
It's not that good. So this is the another multipath which you could see from related to the station location, and some of the residuals which we were looking at some of the stations of the IGS, and because of the multipath from the ground, the variation in the phase residual but there from the TPH file. Okay, so yes, this is general summary. Obviously, we are using the relative positioning. We have the base station, which we call it IGS, and we have our local station. So some of the errors are not dealing. We are not dealing them as individual. We are dealing them in a relative sense. So that's why some of the errors gets reduced. Okay, so yes, the GPS positioning accuracy is a function of two factors. We'll come to that also. So which we call it user equivalent range error or associated standard error is nothing but the component of individual biases you convert it to range term. So that's why we call it user equivalent range error. And this top word, whenever you open or you turn on the receiver, you always have this top value coming in. So how many of you have actually used GPS? So those who are using GPS, the top value is coming up in the bottom, and generally we consider a lower top value, isn't it? So those are properly related to the geometrical figure with respect to those satellite and connecting with the receiver. So we'll see that what do we mean by those figures and how we are accounting these top values. So it is nothing but the word says dilution of precision. Instead we could also understand as a dilution of precision in the estimates at the final estimates. So the more you are prone to the errors, the more will be dilution, just like concentrated and diluted of acids. So simply the dilution of precision. So it is totally based on the geometry of the satellite, how you are looking at the satellites, therefore can be computed without any pseudo range observation being recorded, and equivalent to the strength of figure in surveying terms. And one I came across one of the literature which says that you could also, based on the almanac information or the whenever you are going for the measurements or field measurement, you could also see which satellites are coming at this moment of time and at what time the geometry would be better. So I would go for that particular session so that the results would be much better. So this is the user equivalent ephemeris, ionospheric, tropospheric, relativistic, receiver clock offset, satellite clock offset, multipath noises. So this is actually we are discussing that if the estimation in the range would be very poor, you would be prone to this UERE component at every time. So the dilution type, different type is nothing but geometrical dilution of precision, XYZ, position dilution of precision, or 3D position and time in the GDOP. Position dilution of precision is just only 3D position. HDOP, if you are talking about the horizontal dilution of precision, and VDOP, which is nothing but vertical dilution of precision, similarly to the TDOP also. So at what time would you consider that the estimates of or the DOP value the peaks of the DOP will be there? At what time you would consider? So let's say this is a very fine curve of DOP. It could have been that there are peaks should be much more, and there are actually the figures which are there which are actually more. So what would you relate to if your peaks are there in the DOP plot with respect to time? This obviously because the moment one satellite goes, for that particular time, if your geometry is weak, that peak goes up, and the moment next satellite comes and your geometry again becomes good, the peaks goes down. So that's why you will see a lot of peaks coming up if you plot DOP with respect to 24-hour data. So yes, this is your, how to look at the satellite visibility and geometry is that this is your different satellites. So we don't want that our satellite to be very near to each other. That's why we avoid those kind of situations. Why? So top, which is the position dilution, it less than 3 is ideal for survey work. So when I went to Nainital survey camp, some of you were also there. So initially for a few minutes, it is above 6.3, 6.4. So, and for a quite long time, I would say that for 5 minutes, 6 minutes, it was still 5 points, 6 point something. So we were a little worried that would be because of the altitude, because we have got the exposure to the GPS for the first time. So we'd be a little worried that if it is there for at least half an hour or 45 minutes, what would be there to the data set? But eventually it gets dropped to 2.5 or 2.7 something. So obviously at less than 3 is ideal for the survey work, the high quality work, and below 6 is acceptable, but beyond 6 is not acceptable at all. This is that's why on the first day when I said you cannot take the next epoch data kind of understanding for the, because in the less epoch, and let's say you have only 2 satellite and you cannot take the just 3 epoch data, because eventually that will lead to the poor geometry. So this is also one of the way you could see. And those handheld receivers, Juno 3B or from the Trimble, you could see the scatter plot. It's very, a very well scattered satellite. You could see from that you could understand that DOP value is rising or going above. So that's why in order to avoid those the poor signals, or you could see relate with the phase residual map from that GAMIT session, is that 0 to 10 you don't have any map. There is starting from 10 degrees. So eventually similar to this, you don't want to have any signal to be used if you don't want to have the signals from this particular zones, so that when satellite comes up and when it reaches to a particular geometry, then only you read the data set. Okay, this is the area which I am talking about, which we call it tetrahedron. It's similar to figure in our chemistry which we have used. So this is the geometry of the satellite, and it related with the user in the space this figure is created, and we call it the volume. The more with the volume, the more will be the geometry. So yes, nowadays when you purchase GPS, you also see a manual coming up with the receiver instrument. It is if the horizontal accuracy is 1 centimeter or 1 mm plus 0.1 ppm. What do we understand about this term is that the first term, or which we call it A plus B ppm. So A is the fixed one, and B is varying based on how much you are taking the longer baselines observation. So this is the summary of this slide is nothing but how much absolute and how much relative you are accounting. So for absolute that would be there, but for relative, that 1 ppm, 0.5, nowadays 0.05 ppm you could see, 0.5 ppm you could see. R10 would have much more better accuracy in terms of horizontal estimate. So that could be related with the baseline. So the more the parts per million will multiplied with the baselines. So you could see the relation also in terms of ppm, constant plus ppm and the only ppm. So we are actually using those receivers for our baseline measurement for our work. So that's why we want that. Generally we don't have access to the very high grade quality receivers, but we eventually lie between the so-called receivers which have dual frequency access, but their ppm is around 3 mm or 5 mm plus 0.1 ppm or 5 ppm or 10 ppm. So this is the end of general summary of the errors. Any questions? I would like that we'll discuss, request our Professor Herring also to see those, to look at those plots also. Those are coming for tropospheric delay, for ionospheric delay. Would be happy to see that during our session also, so that we could improve our understanding. So when we get our result, we also have understanding that why the errors are poor, the results are poor, and why the results are better.
showing the graph of that multipath error.